Howdy, and welcome to another Mean 315 auxiliary lecture. So in this lecture, what we're doing is we're working through an example problem of calculating isentropic efficiency. And what I've done here is I've designed a problem that essentially has us looking at the isentropic efficiency of a steam turbine that you would find in a power plant. So we have this steam turbine that accepts steam at a very high pressure, 3000 psi, and 120 degrees Fahrenheit, and expands it to a pressure of 200 psia. We're given the turbine's isentropic efficiency. We're told that it's 80%, and then we're simply asked to determine the actual work and the actual exit temperature from the turbine. So not necessarily given a lot of information. Okay, so in spite of that, it's always good, as I try to emphasize, to start with the same basic protocol, the same basic procedure. And so the first thing that I always like to do is to draw a diagram. And so we can go ahead and draw our turbine. So this is our turbine. And of course our turbine has its exit state down here and its inlet state at the top. And we're transferring some work out of the turbine, and because this is a turbine, that'll be a positive number. And just for completeness, we can go ahead and write that there could be some heat transfer interaction between the system and the surroundings. We'll eventually neglect that, as we'll get to in just a moment, but it's good for completeness to write it down all the same. Then after drawing the control system, I'd like to specifically point out what the control system is, right, or what our control volume is. And in this case, it's basically what we're really analyzing is the water that's flowing through the turbine, the steam. So that's our control system. And I write this down largely to help us remember that we're dealing with water as our substance as opposed to an ideal gas or R134A. We can then go ahead and write down our state information. And so we're given two pieces of information at state I. The first is that we're told that the inlet pressure, PI, is equal to 3000 psia. And we're told that our inlet pressure, TI, is equal to 1200 Fahrenheit. At state E, we're also given information, but we're really only given one piece of information, and that is that the exit pressure is equal to 200 psia. Okay, after writing down the state information, I then like to write down some information about the process, and this is of course a steady single flow work device. That's one piece of information, and that's going to set up a lot of the equations that we use. But the other piece of information that we know about the process is that there is an isentropic efficiency for this turbine that's equal to 80%. And so we want to make note of that as well. And then finally, after writing down information of the process, we can then go ahead and write down the details of what it is we need to find. And we need to find two things. We need to find what the actual work is, and then we need to find what the actual exit temperature is, which I'm going to subscript as TE, AC, the actual exit temperature. Okay, so of course this is basically the information that we have from the problem statement, and so from this point below we're essentially going to be doing our analysis. And so the first thing that we like to start with are the assumptions that we have to make. So we can make a list of our assumptions, right? And these are basically the assumptions that we apply whenever we do isentropic analysis. So the first assumption that we make is that both turbines, so when I say both turbines, what I mean is the ideal and actual turbine. Okay. And the assumption that we're making is that both of these turbines are adiabatic. The second assumption that we'll make is that the exit pressures or the exit pressure between ideal. Actually, let me back this up. Rather than using the word ideal, oopsie, 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 oopsie. I did not want to do that. It's okay. I've got this handy dandy undo feature there. Okay. So anyway, I rather than saying the word between, let's go ahead and say the exit pressure of both devices, or of both turbines, ideal and actual, are the same. And likewise, the inlet state, temperature and pressure, of both ideal and actual turbine are the same. Okay? So those are the assumptions that we'll work under. And of course, this will have implications for our analysis and the approach that we take. And it's going to, we'll have to be rather careful about how we go about this this approach, but it's okay. We'll walk ourselves through that and make it very clear for ourselves. Okay, so it can be a little bit difficult to know how to get started when doing an isentropic efficiency problem. So, and actually for any kind of thermodynamic problem. So the first thing that I usually like to start with is the first law. And I could start with the first law for the ideal turbine, but I'm just going to go ahead and start with the first law for the actual turbine. It really doesn't matter. We would find out that we have to find the same information, and just out of convenience or out of habit, I guess maybe, I started with first finding the or determining the first law for the actual turbine. Okay, so let's start with that. We have our first law equation, and this is going to be the first law equation for our actual turbine. And so this is, of course, our good friend, the first law. So we have little q plus our inlet enthalpy is equal to our actual work minus our actual exit enthalpy. Plus our actual exit enthalpy. Okay, so we already established that both turbines, both ideal and actual, are adiabatic, so our Q term goes to 0. So what our first law tells us is that our actual work, since this is one of the things that we have to find, is equal to HI minus HE actual. Okay, so when I look at this, there's two problems. One, we don't know, or we aren't given, for example, the actual work, right? So we don't know W actual. And secondly, state E actual is not fixed. So we don't know HE actual. So, two unknowns, but only one equation. Well, let's move on and see if we can come up with more equations. So the next thing that we can look at is we can remind ourselves at this point, and again, it doesn't really matter where we do this, so just out of convenience, I do it here, but we recall that the isentropic efficiency for a turbine is equal to the actual work divided by the ideal work. So now I have a second equation that involves actual work. That was one of my unknowns, but I've introduced another unknown, right? I've introduced W ideal, so we can say that our isentropic efficiency, eta st, well, that's given, so we actually know that, but W ideal is unknown. So now we have, in fact, two equations, but we now have three unknowns. Okay, well, again, that's all right. We can now start to see if the first law analysis of the ideal device is helpful for us. So we go ahead and draw our first law equation for the ideal device. And so we have here now, let me just fix this here. Okay, so we have now our first law for the ideal device. And of course, this is going to look just like the first law for the actual device, where we have Q plus HI is equal to now W ideal plus HE comma S. Remember that we use HE comma S to represent the enthalpy from the isentropic process between state I and the ideal exit state, state E comma S. So I'll write that down in just a moment. But before I do that, we can go ahead and manipulate this a little bit to get it into a form that's useful for us. And to do that, the first thing that we recall is that our process is adiabatic, and so Q is equal to 0. And then that allows us to use the first law to manipulate ideal work in terms of the difference between the inlet enthalpy HI and the ideal exit state enthalpy HE comma S. And so we can now at this point say that we can find, so we're starting to make some progress here, right? So again, if I do my number of equations, number of unknowns thing, we now have three equations, right? So before we had two equations and three unknowns. Well, now we have three equations, right? And W ideal is one of our unknowns from previous, the above three unknowns, so that's okay. And HE comma S would be an unknown, except we know how we can get HE comma S, right? So this is what I'm writing down here. We find our ideal exit state enthalpy, HE comma S, by assuming or by analyzing the isentropic process between state I and state E comma S, which is of course the ideal exit state. Okay? So now, how do we get this isentropic process, or how do we get this ideal exit state? Well, we know from the second law, right? And so I won't go through this derivation. We did this in class the other day. But we know from the second law that our ideal exit state entropy, SE comma S, is equal to our inlet entropy, right? This is what we mean by the isentropic process. Entropy is constant. Okay, so we know that, and we also know that we know our exit pressure, right? So we know PE. So since PE is known, that was given to us. And remember that we're taking those to be the same between the ideal and the actual device, right? So PE is the same between ideal and actual. That means that state ES, the ideal exit state, is fixed, right? We know two independent properties. We know entropy at state E comma S, and we know pressure at state E comma S. So we have PE, and we have SE comma S, and we use these two together to determine our ideal exit state enthalpy. Once we know our ideal exit state enthalpy, we can then use our first law equation for the ideal device to determine our ideal work. And once we know our ideal work, we can then use our isentropic efficiency equation to determine our actual work. And this is in fact one of the parameters that we need to determine. And once we determine our actual work, we can then use the first law for the actual device to determine our actual exit enthalpy, HE comma AC. And then by looking up in the tables, once we know our actual exit enthalpy, we can then use the tables to look up our actual exit temperature. And that's the second parameter that we were to determine. Okay, so let's go ahead and do this. We need to do this by first determining our inlet properties, right? Because this all starts by knowing that our ideal exit state entropy is equal to our inlet entropy, right? That then allows us to determine our ideal exit state enthalpy. So the first thing I have to do is I have to determine this inlet entropy, this SI. So let's go ahead and do our state I properties, right? So I can write this down as my state I properties. And my two known properties at state I are pressure, which is 3000 psia, and temperature, which is 1200 Fahrenheit. And I can use these two pieces of information to look up my inlet entropy, which is equal to 1.5850 BTU per pound mass Rankine. And since I know I'm going to need it, right, it appears in my first law equation, I'm going to go ahead and look up the inlet enthalpy since I'm already there. And my inlet enthalpy is 1576.6 BTU per pound mass. And I get both of these values from table A6A. So if you're still having trouble looking up values in the tables, if you see these values and you're not certain where they come from or how to look these properties up, then it's getting very important now that you come and see me about this so that I can help you look these properties up in the tables. Okay, so now let me go to a new page here and continue on with our analysis. So by going to the new page, and let me lift this up to the top here. So now we can also determine our state E comma S properties, just like we did for our state I properties. And so what we know at the exit state is that our exit pressure is 200 psia. And our second property that we know at state E comma S is our exit entropy. Since it's the isentropic process, SE comma S is equal to SI, which we looked up to be equal to 1.5850 BTU per pound mass Rankine. And so now I can use these two pieces of information. Those are two independent properties. I can use those two independent properties to look up my ideal exit state enthalpy, HE comma S, and through linear interpolation in table A6E, I determine that this is 1232.6 BTU per pound mass. And again, I get that from table A6E using interpolation. So again, if you're not familiar or comfortable with how I look this value up in the table and how I use interpolation to get this value, please come and see me immediately so that we can clear these doubts up. Okay, so if you remember from my scheme, I said that once you know your ideal exit state enthalpy, you can then use the first law equation for the ideal device to find the ideal work. And so that's what we'll do now. We can say that W ideal is equal to our inlet enthalpy, HI, minus our ideal exit state enthalpy. And now I know both HI and HE comma S. And so HI is 1576.6 BTU per pound mass. Aren't you happy I had you look that up when we looked up entropy at the inlet state? Minus our ideal exit state enthalpy, HE comma S, which we used linear interpolation to determine as 1232.8 BTU per pound mass Rankine. And so when we plug that into our calculators, we'll get an ideal work that's equal to 343.8 BTU per pound mass. Okay, so again, thinking back on the scheme that we came up with, we said we'll use HE comma S with the first law to find our ideal work, and then we can use our isentropic relationship, A to S, for the turbine, which is equal to the actual work divided by the ideal work to calculate our actual work. And so we simply manipulate this equation so that we directly solve for our actual work. So W actual is equal to the isentropic efficiency for the turbine, A to S comma T, times the ideal work that we just calculated using our first law equation. And so when I plug these numbers in, A to ST was given to us as 80%, 0.8. And our ideal work we calculated to be 343.8. And so when we plug this into our calculator, we'll now get a first result, the first item that we were asked to determine, the actual work, is 275.04 BTU per pound mass Rankine. Excuse me, just BTU per pound mass. Okay, so we've accomplished deliverable number one, but we're also asked to determine what the exit temperature is. And so in order to do that, if you again remember that little scheme I put together, I said that once we know the actual work, we can then go back to our first law equation for the actual device and calculate the actual exit enthalpy from our first law equation. So if we go ahead and do that, we'll recall that HE comma actual, so this is, I manipulated the first law for the actual device here, so this is from the first law, HI minus W actual is equal to our actual exit enthalpy. And so we know each of these terms, so we can just go ahead and plug these values in. HI is equal to 1576.6. W actual is equal to 275.04. And so now our state E actual properties, to finish the calculation, the HE actual is equal to 1301.56 BTU per pound mass. So now we have two independent properties at state E actual. So our state E actual properties. Of course, the first one is still the exit pressure. This is equal to 200 psia. And the actual exit enthalpy, HE comma actual, is equal to 1301.56 BTU per pound mass. And so I can use these two pieces of information to calculate, linearly interpolate from my table what the actual exit temperature is. And what I find is that the actual exit temperature is 560 degrees Fahrenheit. And again, I got that from table A6E through interpolation. Okay? And again, just to reiterate, if you're not seeing how to get these values, how to take these two values of pressure and enthalpy and get temperature out of that with linear interpolation, then it's important that you come see me as quickly as possible. Okay, so that's our second item that we were asked to determine, right? We needed to find this actual exit temperature, and so we managed to do that successfully. Now, what I would like to do very quickly is I would like to show what this means, what this idea of isentropic efficiency means in the context of a TS diagram, and where this, why the actual exit temperature is greater than the ideal exit temperature. Okay, so to show this, and this won't take long, to show this, we're going to draw the TS diagram, right? So this is our TS diagram here. This infamous diagram that we have been studying all semester long, and we'll continue to study it all semester long. So that's our TS diagram. And I'm going to draw the two lines of constant pressure of interest for us, right? So we'll say that this line of constant pressure is, say, for the exit pressure. So we'll say that this is for the exit pressure, PE, equal to 200 psia. And then we'll draw our second line of constant pressure. We'll just say that this one is up here. And we'll say that this is the line of constant pressure for the inlet pressure of 3000 psia. Okay. Okay, so now we'll just go ahead and we'll just arbitrarily say that this is our inlet state, right? So this is our inlet temperature of 1200 degrees Fahrenheit. Here, and so this is state I, our inlet state here. And we know that our isentropic process is a constant entropy process, and so this is going to be just directly below that inlet state. And I did not draw this very well because I'm cutting into my saturation dome, which we know we didn't do, just based on the fact that our ideal exit state entropy was in the superheated vapor table. So I apologize for my poor drawing here. This exit state was actually in the superheated vapor region. But what we do know, right? And so we could say, for example, that this temperature here, again, this isn't the saturation temperature, and so actually, I don't want to mess this up. So I'm just going to delete. I'm going to erase this so that I don't create unintentional confusion here. Not that we ever intentionally try to confuse you, but just so that we for sure don't create any confusion here. Let me just go ahead and move state I up a little bit further here. So now we can draw this over, and I'm going to erase this, extend this down, and we'll just say that this here is 1200 Fahrenheit. So now we'll be well above our saturation region. So we'll say that this now is state I. Now we can say that our isentropic process is directly below this. And so this is state E comma S, right? This is where SI is equal to SE. So I can just try to make that clear by drawing it all the way down to the entropy axis. So this is SE comma S equal to SI. And so this temperature here would be this temperature that we looked up for the ideal exit state, which we actually didn't look up what that temperature was, and I don't have the thermotable with me right now to verify what it is, but all the same, we can also draw on here what our exit enthalpy, or what our exit entropy is, and we can basically show that our actual exit entropy is higher than our ideal exit state entropy. And so we can draw that here and say that this is our actual exit state, since it's at a higher entropy. And so our process actually looked like this. Oops, I'm drawing that at a bad angle. That's what our actual process basically looks like. And so we can then see that our actual exit temperature is, of course, higher than our ideal exit temperature. So this is TE actual, and this down here is TE ideal. And so I'm running out of battery power, as you've just seen, but you basically get the idea from this TS diagram why the actual exit temperature is higher than the ideal exit temperature, because we're still along the same line of constant pressure at the exit state, but we have a higher entropy at the exit state, which moves us further to the right in the TS plane and gives us a higher exit actual temperature, a higher actual exit temperature. And the same would also be true with a compressor, where your ideal exit temperature of a compressor will be lower than your actual exit temperature for an adiabatic compressor. Okay, that completes this example problem for this auxiliary lecture. Of course, if you have any questions, please feel free to contact me. Otherwise, enjoy thermo.